Welcome back. This is, as I had promised, I broke day 4 up into two parts. 4A was regarding doing various limits or calculating various limits. And today we're going to take a look at the second part of that, which is now looking at rates of change in tangent lines. There are two branches of calculus, and one of them is known as the differential calculus, which is what we're doing in this course at the beginning. And then later on, we'll be getting into the integral calculus. Now, the differential calculus has to do with slopes of lines and tangent lines and rates of change, whereas the integral calculus has to do with calculating areas under curves, calculating volumes of revolution, lengths of arcs, all manner of things. And yet, the two calculuses, the two things that are going to be involved here, are very much related, as you will see later on. So let's get started. So the two people that are, and it's controversial at best, that are credited with having invented or discovered, if you wish, the calculus are Leibniz and Sir Isaac Newton. Gottfried Leibniz was a German. He lived in the year 1646 to 1716, whereas Sir Isaac Newton, who lived in Britain, in Cambridge, and was the chancellor there at one point of University at Cambridge, lived from 1643 to 1727. So they would have been about the same age, one's a little bit older than the other, but given the distances that they were apart, one in Germany and one in England, given that email didn't exist back then, and letter writing was done but would have been cumbersome. There's some controversy as to whether these gentlemen communicated with each other regarding the calculus. So it's interesting that they both come up with the same concept essentially at the same time. What we're going to take a look at is how to calculate the slope of a tangent. And what does that mean? Well, I've started off this graph here. Let's say that this happens to be the function f of x right here, going through this point here. Actually, I didn't want that point to be over there. Let me see if I can move this over a bit. Yeah, let's move that over there. And now if I draw my function f of x, let's say it comes up like this. Now, if I want to know what the slope of the tangent is at this black dot here, the issue is we don't know how to calculate the slope of a line when we only have one point. And so what we're going to do instead is to take a look at the y value at x, and that would simply be x, that point there would be x and f of x. And the coordinates of this point would be x plus h and f of x plus h, where h is just some units away from x. So I've shown that here by this green line at the bottom. Now, while we can't calculate the slope of the tangent directly right now, we could calculate the slope of this line that goes between them. And that line is referred to as a secant. A secant. So let's figure out if we can figure out the slope of the secant. Well, certainly in Ontario, the students learned this in grade 9. The slope of a secant would just be f of x plus h minus f of x. That's the difference in the y's, or what they call the rise, divided by the run, which would be x plus h minus x. And this simplifies into f of x plus h minus f of x all over h. Now, keep in mind that what we were after was the slope of the tangent. I'm going to draw the tangent line in here, but keep in mind that we haven't yet seen how we're going to do this. Oops. So if I draw the tangent line in here, that might look like this. And actually, maybe I'll change that to a different color. Let's change that to green. So the tangent, which is what we're after, and can't do yet, could be approximated by the slope of this secant. In fact, if we were to let this h become close to 0, then the slope of the secant and the slope of the tangent. Actually, I shouldn't have drawn the tangent at that point. Let's back this off here. I actually want the slope of the tangent at the point x. So I've chosen a point that's x units away, and the best I can do is to come up with the slope of the secant. But you can see that if we were to let h go to 0, or let this distance, this green line's length, become essentially 0, that the slope of the secant and the slope of the tangent are one and the same. So that's what we're going to take a look at on the next screen. What is the slope of the line through these 2 points? Well, we said that would be f of x plus h minus f of x all over x plus h minus x. And that's the slope of the secant. Now, what we're after is the slope of the tangent. And so the slope of the tangent, which I will just abbreviate as m tan like this, would be the limit as h goes to 0 of f of x plus h minus f of x. And of course the x's here canceled. And so we end up with just over, oops, let's draw this nice and straight here. All over, well, that wasn't supposed to be red, but that doesn't matter. All over h. Now, we'll refer to this in the future as calculating the slope of the tangent from first principles. Okay, slope of the, so this is calculate the slope of the tangent from first principles. You can see how it was important to first introduce limits in this course, because now you can understand what we're about to do with different f of x's. So while we haven't up until now been able to figure out how to do the slope of a line going through a single point, we now have a calculus method of doing it by using limits. So let's take a look at an actual example. What is the slope of the tangent to y equals x squared at 3, 9? Now, not that it's necessary, but I'm just going to draw a rough picture of what this looks like. And so here's y is equal to x squared, roughly. Oops, I should go down a little further here because it goes down through the origin. And let's say 3, 9 is about here somewhere. That's on the function y equals x squared. And so the tangent that we're after is this one. So you can see it's fairly steep and going to be positive from what we can see from the picture. Now, to figure out the slope of that tangent at that single point, you'll recall from the previous screen. In fact, maybe I'll just go and steal this. Actually, you know what? I'll just write it out. So the slope of the tangent is just equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. It's a good idea to always write this out, and that way you'll learn it and essentially memorize it, this little formula. All right, so this becomes the limit as h goes to 0 Now, given that f of x is equal to, this is our f of x is x squared in this case, so that would be x plus h squared minus f of x, which is x squared, all over h. This becomes the limit as h goes to 0 of, and if I were to square that binomial, you get x squared plus 2xh plus h squared minus this x squared all over h. And then, as you can see, something cancel there, namely this x squared and that x squared go away. And I could factor out that h from there. That ends up being 2x plus h all over h. And now the thing that prevented me from determining the limit in the first place, namely we couldn't just let h go to 0 because this function would, or that expression would have been undefined, but it isn't anymore. So now I can cancel these h's, and so we end up getting the limit as h goes to 0 of 2x plus h. Now, given that h is going to 0, and the 2x expression doesn't depend on h, and so this just ends up being 2x. So what does this say? This is saying that the slope of the tangent anywhere, okay, and now I want to emphasize this, anywhere is given by this expression 2x. And so given that it's 2x, if I want to know what the slope of the tangent was at 3, 9, namely x is equal to 3, we just substitute that into here. So we can say, so at x equal to 3, the slope of the tangent is just equal to 2 times 3, or 6, which makes sense. Looking at that, we figure it would be fairly steep and positive. So that was relatively easy, very clever though, because we're using limits here to figure out the slope of a line given only one point, namely at 3, 9. All right, next one. What's the slope of the tangent at x cube of, at 327 of the function y equals x cubed? Again, I'm not going to bother drawing the picture every time, but just so you have a feeling for this, recall that x cubed looks like this. 327 would be there, and so the tangent would be fairly steep. So let's see and positive. So let's do what we did before. So the slope of the tangent is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. When you've done this a few times, you're going to notice a certain pattern to what's happening, as you'll see in a moment. So what is x plus h? Well, that would be x plus h cubed minus f of x. So that would be x cubed all over h. And what does that become? Well, the limit as h goes to 0. Now, if you've learned Pascal's triangle in the past, you know that this binomial raised to a 3 can be evaluated by the following coefficients in Pascal's triangle, namely this one. And so x plus h cubed is just x cubed, that's what that 1 tells me, plus the next coefficient is 3, and the coefficients of, exponents of x will go down and the exponents of h will go up. So that becomes 3x squared h's plus the next coefficient is 3, but this would be x h squared, and then finally plus h cubed at the end, 1h cubed. Then minus the x cubed from the 4 all over h. And you notice that the x cubed and the x cubed here go away, just as previously happened when we were doing it with x squared. Same thing happened there. All right, let's proceed. So this becomes the limit as h goes to 0. And you'll notice that the only terms that didn't cancel are the ones that have h's in them, which is handy because now I can factor out an h from all of them, and that'll cancel this h on the bottom. So we end up with 3x squared plus 3xh plus h squared all over h. The h's cancel, and so we end up getting the limit as h goes to 0 of 3x squared plus 3xh plus h squared. Now, as h goes to 0, this term is going to go to 0. This term is going to go to 0 because h is 0. And 3x squared doesn't depend on h. And so this is just equal to 3x squared. So again, to reiterate again, the slope of the tangent anywhere, okay, I'm emphasizing this is anywhere at any x, is given by the expression 3x squared. Namely, if you know the x, this is the expression that represents the slope of the tangent. So at x equal to 3, the slope of the tangent is simply 3 times x squared, or 27. It's just coincidence that the 27 happens to match the y value. All right, next. What's the slope of the tangent to y equals this quadratic at -1, 2? We'll proceed. Maybe you should do this one on your own. We'll start you off here. The slope of the tangent is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. But this time our f of x is this, right? That's the y is just f of x. So this becomes the limit as h goes to 0 of x plus h squared plus 2 times x plus h plus that 3. And then we're subtracting f of x, which is subtracting all these 3 terms. So that's minus x squared minus 2x minus 3 all over h. I'm going to pause the video here, or you should pause the video here, and try and see what this turns out on your own. All right, if you've come back, and hopefully you've got an expression for what the slope of the tangent was, if we expand those brackets, we end up getting the limit as h goes to 0 of x squared plus 2xh plus h squared plus 2x plus 2h plus 3, then minus all those terms there, minus 2x minus 3. And this is all over h. And once again, you'll notice that any terms that don't involve h go away. So this x squared cancels that x squared. The 2x cancels the 2x. The 3 cancels the -3 there. So any terms that did not have h's in it go away. And this will always happen, assuming you don't make any mistakes in the expansion of f of x plus h. So if I factor out the h from all the terms that survived in the numerator there, we end up with 2x plus and h plus a 2, then everything else is gone, all over h. And then these h's cancel. And so we end up getting the limit as h goes to 0 of 2x plus h plus 2. And as h goes to 0, this term goes to 0 because h is 0, so I can do that. And we end up with the expression 2x plus 2. So once you drop the limit statement, that's referred to as taking the limit. And so the expression 2x plus 2 then represents the slope of the tangent at any x. And so at x equal to -1, the slope of the tangent is just 2 times -1 plus 2, which is 0. Okay, next one. Now, this one is going to be a little messier because of the square root sign there. However, if you can persist through the algebra, you should get this. Let's look at this. Slope of the tangent, limit, as h goes to 0 of f of x plus h minus f of x all over h. Now, the limit, f of x plus h would be the square root of x plus h plus 3. All we're doing is replacing x there by x plus h, minus f of x, which is the square root of x plus 3. That's supposed to be right across like that. All over h. Now, you may think this looks hopeful. How are we possibly going to get an h out of the top there to cancel this h? Well, you'll recall when we did one of the other limits in a previous episode in the series, we talked about rationalizing the numerator. And so that's what I'm going to do here. And just to save time, I'm just going to multiply by the conjugate of the top, which is the square root of x plus h plus 3 plus the square root of x plus 3, all divided by the square root of x plus h plus 3 plus the square root of x plus 3. And that's just like multiplying by 1 because we got something over itself. And so that's perfectly legal. We haven't changed the expression at all. However, the numerator turns out to be nice. Recall that the top looks like a minus b times a plus b, which gives us a squared minus b squared, right? A difference of squares factors. And so I end up getting the first thing squared, which removes that radical sign. So there's the a squared part, minus the b squared, which would be just x plus 3. So we're subtracting x and then minus the 3, all over Now, don't worry about multiplying all the stuff out at the bottom there. Just write it out like this because something nice is about to happen in terms of the taking the limit. All right, you'll notice that the x's cancel as promised. The 3's cancel. And so we end up getting just h over h. And so these h's cancel. And so I end up just getting the limit as h goes to 0 of 1. All that will be left on the top is a 1. And on the bottom, we've got the square root of x plus h plus 3 plus the root of x plus 3. And now we can take the limit. And this just becomes 1 divided by square root. If h goes to 0, this first radical becomes just x plus 3. And then I'm adding another root of x plus 3. So it's 2 root x plus 3's. And that would be the final answer. In one of the other questions coming up, we'll take a look at that once we know how to calculate the slope at a point, to actually calculate the equation of the tangent at that point. Let's move on. This one says determine the slope of the tangent to each function at the point indicated. To each function meaning there's one here and there's going to be one on another screen. Now I've graphed 3 over x, which is reciprocal of a linear function, so hopefully you're familiar with that. That's the blue curves there. And at x equal to -2, which would be right about here, right there, I've drawn the slope of the I've drawn a tangent in, so you can see what it is approximately. And we're going to try and see if we can figure this out. All right. So once again, slope of the tangent is equal to the limit as h goes to 0 of f of x plus h, x all over h. Our f of x plus h this time will be 3 divided by x plus h, that's f of x plus h, minus f of x, which is 3 over x, and then all that is being divided by h. Now, if you've not been good with dealing with fractions, you may have some difficulty here, but hopefully that, and certainly in a Calculus AP course, you should be good with fractions. So we'll leave that h on the bottom there. And the top part, I need a common denominator. So that would just be x times x plus h. And so this numerator just becomes 3x minus that 3 times that x plus h. So this becomes the limit as h goes to 0 of, let's see, the 3x minus the 3x would go away. Then we end up with negative h on the top. Oh, sorry, negative 3h on the top, divided by x times x plus h. And since we're dividing by h over 1, that's like multiplying by 1 over h. So I'll just introduce the h into this denominator. And now you can see that the h's cancel. And so I end up getting, oops, I don't need it to be green. That ends up being the limit as h goes to 0 of negative 3 over x squared plus xh. But as h goes to 0, this term is going to go to 0 because h is 0. And so we simply get negative 3 over x squared. Okay. Now, we're supposed to be calculating the slope of the tangent at x equal to -2. I'll just move this up here. At x equal to -2, the slope of the tangent would be equal to -3 divided by -2 squared, which is -3/4. Makes sense looking at that picture that the slope would have turned out negative, which it has. And if I actually wanted to calculate what that point was, the slope of the equation of the tangent at that point, this point over here is -2, and if x is -2, then the y value is just -3/2. And so we really just want to calculate the equation of a tangent which has a slope of -3/4 and goes through that point. So y is equal to mx plus b. We sub this in for the slope, and this is our x and y that we want to use in this equation. So I end up with -3/2 is equal to -3/4 times x, which is -2 plus b. And then we end up getting negative 3 halves is equal to negative 29 is positive. So this is 3 halves plus b. And so the y-intercept is just negative 6 halves, which is negative 3. That makes sense. Seems to be going through negative 3. And so the equation is y is equal to, the slope was negative 3/4 x plus the b, which is negative 3. So that would be the actual equation of the tangent at x equal to negative 2 for the function 3 over x.